In this video, we're going to look at what happens when a chair actually flips from one form to another, the actual chair flipping process. We're going to consider energetics and look at things structurally. What I'm going to start with is my model of a six-membered ring. So this looks like a cyclohexane, right? And it's got the black balls represent carbon, the white balls represent hydrogen. There are two hydrogens on each carbon, so it looks like cyclohexane. We can do a better job of depicting this structure by considering a chair. You'll have to forgive me 1 second. It's always like it's a bit awkward at first for me to rotate this into a chair structure. It's always humiliating every time that I do it. That's a pretty, for as long as, I like these bonds to be a little bit longer. You'll have to excuse me. I like these bonds a little bit longer, but what I notice about, let me get my fan here. What I notice is when the bonds are long, which is helpful for some other applications, it's harder to see the chair structure. But my microphone out here. But at least I did it, and maybe I'll consider the smaller version. I'm just gonna get these flaps puckered. There we go. You can kind of see a structure of a chair, and that does allow us to get to a lower energy state. How I got there, though, was several twists and turns along the way, rotations of carbon-carbon single bonds, which are important to consider as we're drawing this on paper. That is, as we do a chair flip, that's a conformational isomerism, just a free rotation over carbon-carbon single bonds. So the topic of today is, how does chair flipping actually occur? It's quite exciting outside my window, I should add. There's a very competitive cross-country meet right outside my window. So if we hear some cheering, it's probably because chair flipping is that exciting, or somebody's finishing the race. So how does chair flipping actually occur is what we're looking at. Okay, so as I mentioned, and I've said several times, it's a series of free rotations over carbon-carbon sigma bonds. And sigma bonds, again, are single bonds. Okay, so what actually happens here? Well, what I'm going to first do is consider a chair structure. And before, as we do the chair flip, what ultimately happens is we're going to flip each of the flaps, the left flap and the right flap. We'll pick one to go first. It doesn't really matter which one. I'm going to turn on the fan just to drown out a little bit of the cross-country meet sound. It doesn't matter which flap that we choose to flip on this for the first part. We just need to flip one of them. What we do is we do a partial kind of flip where we rotate the central carbon-carbon bond simultaneously to position this flap upwards. This is all in equilibrium. So I'm going to draw my two half-headed arrows moving in the opposite directions to show equilibrium. Then what I'm going to get is kind of a half chair. So I go from a chair to a half chair conformation. And then from this half chair conformation, which actually, if you look at it, it's not as hard to draw as a chair structure, but this next one gets a little zanky. That's not a technical term, I should add. This next one, I lost a carbon here. Where did I lose that carbon? I'm going to start over. I'm very sorry. It's just the twist boat is hard for me to draw. And then from the twist boat, I'm going to add here, don't worry about this structure. And I say that because I've never really had to worry about that structure. And as you can tell, I'm not good at drawing it, whereas the other structures I'm a little bit more comfortable with. So we'll move on from the twist boat very quickly to this structure. And now what you'll notice in this structure is both of the flaps are flipped upwards. And we call this structure the boat structure. And that's where the boat in twist boat came from. Otherwise, boat seemed a little random. Now it seems less random, right? Because if you look at the structure, I should draw this in a separate color so people don't get like too excited. But there is a person, and they're on a boat. And I am guessing that every year I've taught this, people get that reference less and less. If you need a break, you could Google on a boat. It's a fun music video. Okay, anyway, so back to this. We're going to go from the boat structure into a twist boat. And from a twist boat to a half chair. And I'm not going to draw that other twist boat because it's not something that I'm proud of myself when I draw twist boats. Okay, then we're going to get to a half chair. Now you'll notice this half chair is different from the other half chair in that it's now the right flap that's flipped upwards. And then at this point, we flip the other flap downwards and we have a chair. And this chair has been flipped from the original. So my point here is that when we go from a chair, one chair, to another chair, and maybe I'm drawing these like super thick highlightery equilibrium arrows, as we go from one chair to another through the chair flipping process, there are several intermediates along the way. Excuse me. There's a half chair twist boat, a boat structure, another twist boat, and a half chair. So it's kind of like a little bit of an exciting place that the chair structure gets to go to. And man, these twist boat structures are just bothering me. So I just need to find a good, I've never pushed myself this hard to find a twist boat, but if this ever gets immortalized, I want to make sure that I draw this effectively. Whoops. So we have, in the twist boat structure, we're going to have, well, that wasn't so bad to draw. So this is my twist boat structure. I mean, it's kind of weird the first time you see it, and it's not super useful, and we'll see why in just a second. But so we have several intermediates along the way for our twist boat structure towards our from our chair structure to a half chair to a twist boat to a twist boat to a half chair back to a chair flip. And so there's a lot of information here. Let's start with, what do you need to know? So what do you need to know? That during a chair flip, and now there are children crying. This is the noisiest video I've ever done. During a chair flip, several intermediates are involved. Most namely a boat. And we'll see here that my classification of boat as an intermediate may be misleading. With all these intermediates, we can get to something that we may, at this point in the semester, be missing, and that's the energy diagram. The energy diagram. And so we're going to be doing an energy diagram for chair flipping. So in the energy diagram for chair flipping, what we see is that, I'll get this back on the screen here. No reason to get too far ahead of myself. If we have an x-axis that is reaction coordinate and a y-axis that is energy, And energy could be free energy, sure. What we're doing is we're saying, how do we get from one chair, I guess I'll have this version, to another chair? And those chairs, because we have a cyclohexane with no added groups on it, those chairs are equal in energy. There's not one that's preferred, they're the same. Going from one to the other is not necessarily, excuse me, a spontaneous process. Okay, so what we do is we first go up in energy from a chair structure to a half chair. And then from a half chair to an intermediate, which is a twist boat. I feel like I've drawn the left half of this beautifully, but I'm running out of space. So I need to fit all of those intermediates. Okay, power of technology. From the twist boat, we're going to go up slightly in energy, and then down again to the other twist boat. Now this mountain, shallow mountain, I guess, between the two twist boats is the boat structure. Okay, we have the boat. And remember, the boat structure doesn't automatically generate a person. Sorry, I'm hilarious tonight, I guess. Okay, so then we go up in energy and down to a chair structure. So we'll go chair to half chair. There's some symmetry in this because there's no groups on the ring. So one half chair looks the same as the other half chair, whether you have the left pucker up or the right pucker up, it doesn't matter. But what we see is that we have two intermediates, the twist boats. Those are the intermediates. And the boat structure, along with the two half chairs, are the transition states, where it's the energy of the half chairs, the activation barrier to the half chairs, that determines the rate of chair flipping. So the rate of chair flipping is controlled by the half chair energy. It's sort of like the transition state for the rate determining step. Okay, so it's that step that it's both of those transition states that control the rate of the reaction. They're equal in energy, so it's really not super productive to worry about which individual one is controlling the rate, but suffice it to say, its energy is what's controlling the rate for the reaction. So another thing that we need to know is we want to know that the boat structure is a transition state. For chair flipping. So the boat structure is fairly famous, and that's one that I would hold on to along with the chair structure. It's definitely not the same level of importance as a chair structure, not by any means. It's just an important one to sort of hang on to. So that'll do it for this video. Just looking at how chair flipping actually occurs. We go from chair to half chair to twist boat to twist boat to half chair to chair. Just so we can see that there's several intermediates involved. It's not like some spontaneous event, excuse me, spontaneous isn't a great word. It's not some concerted event where everything sort of happens at once or in concert and all the bonds rotate all in one fell swoop. It's a series of carbon-carbon rotations. We rotate as much as we can within each individual step, but we're going to hit some valleys and some hills in our energy diagram along the way. In the next lecture, we'll look at kind of a deeper analysis of these free rotation events that happen during chair flipping.